Assalamu alaikum wa rahmatullahi wa barakatuh, and hi everyone. My name is Rayyan Muhammad Hamdi Al-Hartani. I'm doing Bachelor of Mechatronics Engineering, and this is my FOAP title, which is Development of Object Localization Technique using Deep Learning Inspection. In this project, we will have introduction, literature review, research methodology and result, and conclusion and future work. Recently, artificial intelligence and machine learning became widely used, and they became the core of the recent industrial development and from the main components. And one of the main problems of the machine learning is the object localization in an image. It was difficult to localize an object in an image, but with improving the methods of deep learning and machine learning, it became easier, faster, and more accurate. In real life, robotic arms have some errors and failures. It may lead to bad conditions and accidents. These accidents may cause damage in products, buildings, and even humans. Our objective in this project is to investigate typical used methods and compare it with the result we get. Secondly is to develop method of object localization using deep learning and using Python algorithm. Lastly is to evaluate the result of our developed method with other methods we have been investigated. We have many scopes for this project. First one is the object of this project is the robotic arm. Secondly, deep learning software will be used in this project, and especially we will use the Python algorithm. And finally, we will search and analyze data, and we will look for a dataset from the internet. Our literature review have some journals related to object localization, but with different methods, like the first one using SIFT, which is Scale Invariant Features Transform method, the second one using RGBD method and LDLEM, third journal using Self-Product Guidance and Masks ILSVRC method. This journal using multi-methods. First, multi-scale sliding window. Second, implement within ConvNet. Third, localization using predict object boundaries and bounding boxes. Now we have the methodology flowchart. So the first step is to add an image to be processed. After we collect our dataset from the internet, we need to pre-process each image. Then the next step, it will be the pre-train and label the image by using PyTorch. So we will label each part we need to localize. The next step is to train the method to label the image and the parts automatically. The last step is using the YOLO version 5 algorithm to detect and localize each labeled part, and that will be the end. PyTorch is a high-level adoption within deep learning framework community. It shines for a rapid prototyping with dynamic neural networks, auto differentiation, deep Python integration, and strong supporting for GPUs. It also enabled fast, flexible experimentation and efficient production. PyTorch is mainly used to train deep learning models quickly and efficiently, so it is the framework of choice for a large number of researchers, engineers, and developers. YOLO is a short form for You Only Look Once. It's an object detection network. The object detection task entails location and classifying certain items in a picture. Previous methods like RCNN and its variants required pipeline to complete this operation in several phases, because individual components must be trained independently. This can be slow to run and difficult to optimize. YOLO is a single neural network that can handle everything. To make it simple, you can take an image as an input, pass it through a neural network, looks like a normal CNN, and you get a vector of bounding box and class prediction in the output. Here we have some advantages of using an algorithm of YOLO v5. First, this is the first native release from the YOLO family written in PyTorch, and as we mentioned in the previous slide, PyTorch is easier and faster. It's become more widely known as a research framework. YOLO v5 may be easier the border of research community. This also makes a deployment to mobile devices simpler, as a model can be compiled to ONNX and Core ML with easy. In this slide, we have a compare between YOLO v5 and YOLO v4 in terms of FPS or frames per second. And as we see here, it mentioned about a batch. The batch here will be the number of the image that will be used in a training in a certain time, and here we use the second. So as we see, we have YOLO 5 could achieve 140 frames per second, but YOLO v4 achieved only 50 frames per second, and that shows the difference. The third point of comparing between YOLO v5 and YOLO v4 will be about the accuracy. So as we see in the end, but it's rare to see such across the board performance improvements without any loss in accuracy, and that belongs to YOLO v5. Next step is about comparing the size. So YOLO v5 is much smaller than YOLO v4. YOLO v5 is only 27 megabytes, but YOLO 4 is 244 megabytes. So it's nearly 90% smaller than YOLO v4, and it deployed embedded device much more easily. The project will use images from the internet as an input, and for the output Python algorithm we use some functions, and here we have some functions like numpy, which is Python library used working with arrays, like src, which is source input image, dsize, which is describe the size or the output image, fx, which is the factor along horizontal axis, and fy is the scale factor along the vertical axis, and last one, which is the interpolation. To get our result, and as we mentioned before, we need to collect some datasets from the internet, and this image is an example for that dataset. After we collect the data from the internet, we need to check its sizes. So in our project, the size is 255 pixels for each image we used. So in the image given here, we have three labels, which is hand, arm, and base. To train the image to get those labels, we need to use PyTorch, and that's what we have done. After we labeled the dataset in the image we have before, we do the localization for the labeled image using YOLO 5 algorithm. And as we see here in the table, this table represents the localization for each boundary box for each label. And as we see here, the base and the arm and the second arm and the hand, it belongs to the photo or the image we have shown in the last two slides. It is the localization for each label for that image. In conclusion, in our labeling, our algorithm was able to label all the parts of the image in our dataset using the pie chart. And the localization was done using labeled and trained dataset to get the localization based on each label box or boundary box that contained a labeled part, and the table in the previous slide was an example for a localization for each box of the labeled and used images. For future and in terms of improve the result, it's recommended that you have to use a large number of images and big data.